Today we study electrostatic potential. Until now, we have studied the Coulomb's law first, and by making use of the Coulomb's law first, we have defined the electric field, and electric field can be computed based on the Coulomb's law first. In addition, if there is a symmetry in the charge distribution, it is very easy to compute the electric field by making use of Gauss' law. And today we study electrostatic potential. The electrostatic potential V at a point P in the electric field of a charged object, this is defined as this kind of form. Here, in the numerator, W infinity is the work done by the electric force. So there is a negative sign on it. So this is a negative minus work done by the electric force. On a positive test charge, Q divided by Q0. So potential is proportional to the work, electrostatic work done by the electric force. Then we put the negative sign on it. From an infinite distance to P. So there is a charge Q fixed here. Suppose that we have positive charge. We have charge Q0 is 1 Coulomb, is a positive, and at infinity, because the Coulomb's law states that force is proportional to the inverse square, and the distance r goes to infinity, that there is no force at all. But from infinity to bring this particle to here, we note that the displacement and force, electrostatic force, both of them, Q is Q times a small Q0. This is a positive. The electrostatic force is repulsive because the electrostatic force is repulsive. Force is opposite to the displacement. Thus, the work done by the electrostatic force from infinity to some position, let's say this is R. Here, infinity, from infinity to this position. The electrostatic force, the displacement, and force, they are opposite. The electrostatic force is negative. But the work done by the electrostatic force from infinity to a certain position is negative. So we attach the negative sign on it, and we rescale it by the charge Q0. Then we obtain the electrostatic potential. Okay? If we carry out some work on the system, then the system obtains some energy. So because the work done by the electrostatic force to the system is positive, from infinity to a certain position, it is changed into an electrostatic potential energy. This is electrostatic potential energy. So negative of work done by the electrostatic force is electrostatic potential energy. You remember potential energy, it can be computed by the conservative force, that displacement, put a negative sign on it, to a certain position from a reference point. And here we have reference point is infinity. At infinity, electrostatic force and electrostatic potential energy completely vanishes. That is our convention. But we do not have to put it a zero. It is an arbitrary constant at a reference point. C. The electrostatic potential energy stored in the test charge of the system is, this is energy. Electrostatic potential energy. And the right side is potential. Electrostatic potential. So this is energy and this is potential. So we have scaling factor charge Q of the test charge. It is just like the relationship between the electrostatic force and electric field. And charge is multiplied to have electrostatic force. So, electric field, electrostatic potential is independent of the magnitude or sign of the test charge. So it depends only on the charge distribution, except for the test charge, the surrounding charge distribution. If a charge Q experiences a potential difference delta V, then the potential energy changes as because U equals QV at a certain point, we have U2, QV2, the difference from this is delta U equals Q delta V. And here U2 minus U1, this is V2 minus V1. E. If a charge Q experiences a potential difference without any external forces, then the change in the kinetic energy is determined by the conservation of mechanical energy as total mechanical energy is the sum of kinetic energy plus potential energy. If there is only a single force applied to the system, then the potential energy is completely depending on the electrostatic potential energy. And this is the kinetic energy, potential energy, and the difference must be zero must be 0. Therefore, kinetic energy change is negative. Kinetic energy change is negative of potential energy change, because potential energy change is like that. We can substitute in here. So potential energy change is negative of the change in the total kinetic energy. F. If a charge Q experiences a potential difference in the presence of the work done by an applied force, the change in kinetic energy is like that. Okay. This is additional force, additional work that is independent of the electrostatic force. Then we have additional P's to change the kinetic energy. Number 2, electron volt. Electron volt is defined by elementary charge E. Elementary charge E is 1.602176 times 10 to the minus 19 Coulomb. I told you it is the exact number. And volt. So this is Q. And volt is a unit of potential. So charge times potential. Charge times potential is energy. This potential. Potentials V is sometimes written as a volt as a unit. It is actually electrostatic potential. All right. So electron volt is energy. Q times V. The charge of an electron is a minus E, while that of the proton is a plus E. So if there is a potential difference with the same amount for proton and electron, the energy change is opposite in sign, because the delta U is charge times potential. And if this potential is the same, proton and electron, they have opposite sign. Electron has minus E, proton has plus E charge. Number 3, a charge minus Q of mass m enters into the region between the two parallel plates with the initial velocity v0. So initial velocity v0, as shown in the figure. The surface charge density and the potential, so V equals 0, and surface charge density is minus sigma at x equals 0. And this is x equals d. This plus sigma in here, and v equals 0, so this is v. Right? We assume that the electric field between the plates is uniform and neglect any other forces. Electric field, two charged plate, we assume that sigma is a positive, then electric field is along this direction. This is E. And this is a plus charge, minus charge. So we have a negative side, and outside is 0. Remember, a plate with surface charge density sigma emits the electric field sigma over 2 epsilon 0, sigma over 2 epsilon 0 outward. And because there are two plates, the resultant electric field inside is sigma over epsilon 0, and outside is vanish. So sigma minus sigma. Alright, the electric field is like that. And then electric field is constant. So we have V equals 0. Right? We want to know the potential in here. Electric field is in this direction. V, if I want to compute the delta V, then from 0 to dx equals d, dx minus electric field dx, right? And minus the electric field dx vector is I hat dx, and minus E vector is because E equals minus sigma over epsilon 0 I hat minus E equals sigma over epsilon 0 I hat. Therefore, this one 0 to d sigma over epsilon 0 dx. So this is a sigma d epsilon 0. As a result, actually delta V is V because this reference point potential is 0. So what we obtain is V equals a sigma d over epsilon 0. Therefore, you can rewrite this one sigma equals epsilon 0 V over d. This is an expression. The change in the kinetic energy of Q from 0 to d is QV. Yes, there is no other force except for the electrostatic force. The kinetic energy change is completely depending on the electrostatic potential energy. If this charge, this mass is positive, then the kinetic energy decreases. If the charge of this particle is negative, then this particle accelerates, so change in the kinetic energy is positive. Four, the electron accelerates from rest to, the change in the kinetic energy from rest. So delta K is 1/2 mv squared final, is 1/2 mv initial squared, and rest means v initial equals 0, so this one vanishes. So delta K is 1/2 m final squared. So this is electron. So we put subscript E to identify the mass of the electron. And the electron has kinetic energy change is minus the potential energy change, and minus potential energy is QV, and Q of the electron, Q equals minus E, therefore it is E delta V. And delta V, we use the potential difference V, so delta V can be identified as EV. So we substitute the right side. Therefore, solving this equation, final speed of the electron can be found like that. Alright. Equipotential surfaces and electric field. Equipotential surface means any points on a single equipotential surface have the same electrostatic potential. Aha. V equals 1 volt, 2 volt, blah blah blah. Okay, that means these 2 points has delta V equals 0. Any 2 points on the equipotential surface, potential difference is 0. Okay, so these are equipotential surface. Under the motion of a charge on an equipotential surface without any external forces, the speed of the charge is invariant because this relation, potential difference is 0, then kinetic energy, potential difference is 0, then kinetic energy does not change at all. Electric potential difference. So delta V, you record energy shift is minus force potential energy. So we rescale this one with the charge Q, then potential difference is minus electric field integral. Okay? From initial, final. Sure, in general, it is a vector. If the electric field is uniform, then this one becomes minus uniform electric field and displacement. You can apply this basic theory to solve problem 3 and 4. Let me go ahead with the study explaining the electrostatic potential of a monopole. The Coulomb's law of force and Gauss' law gives the electric field generated by a point charge placed at the origin is given like that. You'd like to compute the electrostatic potential directly from the electric field by making use of the definition delta V equals minus x initial x final electric field dot dx. As I told you, xi is put to infinity and an uncertain radial direction. So that means r goes to infinity. As r goes to infinity, we choose v r limit r goes to infinity equals 0. So what we want to do is there's charge q at the origin. We have a certain distance of field point P and reference point r goes to infinity. So assume that Q is a positive. Electric field is a radial direction. So electric field is in this direction and displacement dx is along the radial direction from r goes to infinity to here. So we integrate over this path. Alright, we substitute the electric field. This is the electric field. This is a radial direction. We substitute this electric field in here. And dx is dr unit vector of radial direction. So if I multiply this one, this E dot dx, then we have over factor 1 over 4 pi epsilon 0 q over r squared times dr r hat dot r hat. This is unit vector scalar product. This is 1. So we end up with this result. And we have additional negative sign on it. Therefore, we have over constant vector down, and integration is from the reference point at r goes to infinity to the point P that has the distance r from the origin. And this negative sign is multiplied to this 1 over r squared to have minus 1 over r squared. Okay, 1 over r derivative is minus 1 over r squared. Therefore, this integral is actually infinity to r d 1 over r. Okay, that means 1 over r evaluated at r, and evaluated r goes to infinity. So this contribution vanishes as r goes to infinity, and the result is this. So electrostatic potential V is exactly the same as the electric field, except that the power is 1 over r instead of 1 over r squared. And in addition, electrostatic potential is a scalar. electric field is a vector. So the scalar is easier than the vector to treat. Just like the case of electric field, electrostatic potential is also additive. So combination with electric charge generates the resultant electrostatic potential that can be obtained by simply adding the whole contributions. If there are many charges, n charges, for example, Q1 is placed with the distance R1 from the origin, Q2 is placed with R2 from the origin, Q3, R3, and so on. Have Qn with the distance Rn, then the resultant potential energy, the resultant electrostatic potential is just the sum. All right. Number 3, conducting shell of radius r centered at the origin is uniformly charged with Q. Conducting shell of radius capital R. Now the electric field inside is a 0. Right? The shell of charge uniformly charged with the like that. The electric field radiates the radial fraction. We compute the electrostatic potential. We carry out the same integral. This integral to find that v equals 0 at r goes to infinity, and potential increases as 1 over r, proportional to 1 over r. And from this is r, as soon as you reach the radius of capital R of the shell, there's no electric field to integrate. So inside, the potential electric field is 0, so delta V equals 0. Everywhere is a potential, the equipotential. Therefore, it is something like that. It's frozen. Okay, proportional to 1 over r, and it is fixed to 1 over capital R. Sure, over factor is the so therefore the result for the electrostatic potential, depending on the radius r, is given like that. You can generalize this idea for the case the electric field due to a non-conducting sphere of radius r. That means charge distribution is uniform inside the sphere. Then you can simply follow this calculation to verify the result. This is an example of computing the electrostatic energy of a complicated system, many charge distribution. The electrostatic energy, potential is 104 pi epsilon 0 Q over R. What is the potential energy? If it is Q, let me call this Q1 and Q2. What is the potential energy? The potential felt by Q2 is Q1, and potential energy of Q2 is Q2V, that is 1 over 4 pi epsilon 0 R Q1 Q2. What happens if I have many charges? R1, R2, R3. It's better to A1, A2, A3, Q1, Q2, Q3. Electrostatic energy of the whole system is 1 over 4 pi epsilon 0 common factor. Here, Q1, Q2 has the distance A1. Q2, Q2, Q3. Q2, Q3 has the distance A3. And Q3, Q1. Q3, Q1, A2. This is the electrostatic of this three-body system. Let us compute the electrostatic potential of a dipole. Electrostatic potential of a dipole can be computed by simply adding the two contributions. One contribution due to the positive charge, and the other contribution due to the negative charge. We assume that this two charges plus Q is at 0, 0, this x, y, z component, 0, 0, half of d, minus Q is at 0, 0, minus half of d. Then we know that the electric dipole is Q times D. D is the separation. So from minus plus. This is the separation. So Q times D is an electric dipole. And we choose a field point. Here at x, y, z in general. Then the electrostatic potential at this point is plus charge Q, 1 over 4 pi epsilon 0 Q over R plus. And we have negative sign, negative charge, minus Q, and distance. This one is R minus. This is the electrostatic potential of the whole system. So it is easier to compute than the electric field of the electric dipole system. Okay, this result is written in here. Okay. Now we can apply the binomial theorem. binomial expansion. And t, we choose d over r is a very small, much smaller than 1. This d is much smaller than the r. R is the distance. R is the distance from the origin to the field point P. Then 1 plus t to the power a. A can be any real number as long as absolute value of t is much greater, smaller than 1. But expansion is converging very fast if t is very small. However, it doesn't care as long as the absolute value is less than 1. However, we must not consider the case t is greater than. In this case, we cannot apply the binomial expansion. The series does not converge to a certain value. Alright. Then the coefficient is a. This is a. First one is a, and the next one is a minus 1, 2 factorial, and the third vector is a minus 1, a minus 2, 3 factorial, and so on. What happens if we substitute a equals minus 1/2? Then this is minus 1/2, and this is minus 1/2, minus 3/2. So minus minus plus, plus 3/8, and so on. So we apply this expansion formula by making use of the binomial expansion field. If we keep the correction term to 1 over r and neglect the terms of order d over r squared or higher, 1 over r plus minus is actually like that. This is r vector. So r plus vector equals r vector minus half of d, right? And r half of d r minus vector. So r minus vector is r plus 1/2 of d. Therefore, r plus minus equals r minus plus. Okay? So, if we expand this one, we have r squared minus plus r dot d. We have neglected d squared term. And then we factor out absolute value of r, then the expression becomes like that. And substitute in here, keeping t equals minus plus the d over r cosine theta. So this guy is plus minus d over 1 over 2 to r cosine theta. Alright, so substitute this result in here. We obtain 1 over the first term cancel exactly, and second term is double because they have a different sign, but we take the difference. So what we have is this one. Electrostatic potential of a dipole system with the leading approximation is like that. We can take the derivative to find the electric field from this expression directly. Previously, we computed the electric field due to the dipole only along the z-axis. So origin minus 1/2 of d plus 1/2 of d, charge q, charge minus q, and we compute the electric field along the z-axis. But this expression is quite simple. We can compute the electric field everywhere, because we have field point for any x, y, and z. The electrostatic potential of a charge distribution can be computed in more general cases. Suppose the charge distribution is along a curve. What we want to do is a sum of everything, 1 over 4 pi epsilon 0 delta q r. This one becomes an integral. Small dq is placed at r. And this is the field point. Here, this is a scalar. So, because scalar is much easier to treat than the vector, so computation of electrostatic potential is much easier than the direct computation of the electric field. So, in case charge is distributed over a curve, then density, linear charge density multiplied by the differential of the length. If the charge is distributed over a surface, dq is expressed in terms of surface charge density multiplied by the area, differential area. If the charge is distributed over the space, then dq of differential charge is expressed as a product of the volume charge density rho multiplied by the differential volume dv. Okay, let us compute the electrostatic potential due to a line charge. There's a uniform charge distribution along the x-axis. We have this length is L. This length is L. And charge capital Q. So charge density is charge Q divided by length L. This line charge density. If we use line charge density, uniform line charge density, a thin rod of length L uniformly charged with Q. So lambda is a constant. And differential of the charge along this path, or along this line segment, dx is like that. Here we introduce the hyperbolic sign. Sine hyperbolic is defined like that. You can solve this quadratic equation. This one can be expressed in terms of y, with substituting y equals exponential x. Then you have quadratic equation. The solution of quadratic equation, this quadratic equation for y, can be obtained in this way. This e to the x is y. Because this is x equals log t plus 1 plus t squared. Log is natural log. That means log is written in an natural log. That means log whose base is e. E is not an electron charge, but the Euler's number. That is okay. You carry out some algebra to find that you can construct this kind of integral table. This is very important integral table to evaluate the electrostatic potential. Alright, so you follow this calculation, you end up with this one. Therefore, this is related to the inverse sine hyperbolic function. Finally, substituting the explicit value for the range of x ranges from 0 to capital L, you'll find the electrostatic potential of the system is expressed in this way. Using a similar method, we can also compute the electrostatic potential due to a disk. Again, we have very similar integral. Let's see. This charge, uniform charge distribution over a disk of radius r. So sigma is charge divided by area, pi r squared. What we want to do is to find out the potential at some point z that has a perpendicular distance from the disk, and that is along the symmetry axis of the disk. The charge q, differential dq of the differential charge can be obtained using the symmetry of the system. We choose annular region of radius difference by d rho. Then the area of this annular region is this width is d rho, and the length is d rho, and length is 2 pi rho, and this area which is the same as d rho goes to 0. Using this representation, we find that this 2 rho d rho appears if I take the derivative of rho squared plus g squared. This is rho, Z, and this is rho squared plus Z squared. Scale it. Okay? Rho Z rho Z R is a rho squared plus G squared, square root. Okay? So you can follow this. So this is the R. This is R. Right? And again, the potential is evaluated by dq over R integral. And this is R. Right? So we have Z squared dq, and dq is like that. 2 rho d rho integral multiplied by 1 over 4 pi epsilon 0 and additional factor. But this is the most important part to evaluate. So that integral is simply expressed in terms of this form. In comparison with the computation of the electric field, electrostatic potential due to uniformly charged disk is much simpler than that of the electric field. Anyway, this integral is trivial. It is just total differential, so the final result for the definite integral is simple. And if we substitute the radius, rho ranges from 0 to capital R, so final result is like that. If we take the limit, R goes to infinity, we find that the potential V reaches infinity. However, if we take the derivative with respect to Z, that infinity cancels and the physical value of the electric field remains constant for a given value of Z. Okay. Computation of the electric field from electrostatic potential involves the calculation of the gradient. Gradient operator is defined like that. It contains partial derivatives along the x-axis, y-axis, and z-axis. So, gradient, for example, I hat is a unit vector along the x-axis, and we take the partial derivative with respect to x and multiply the unit vector along the x-axis, and so on. So this is the gradient. And electric field is defined by minus gradient of potential. Minus gradient of potential. We know potential electric field, this positive charge electric field is going out. Okay? Electric potential increases 1 over R proportional to. So if you approach the charge, potential increases. The electric field is the opposite direction of increasing potential. Therefore, what we want to do is take the gradient to find the steepest path of increasing the value, put the negative sign on it, so that the electric field is along the direction, the along which the electrostatic potential decreases most fast. All right. If you use the Cartesian coordinate, the differential along the x, y, z axis are like that. You can do the same job in various coordinate systems. Anyway, in the cylindrical coordinate system, we have z direction and radial direction, that is rho, and phi, that is azimuthal direction. Anyway, in the case of planar radial direction, the displacement is expressed in this way. Displacement along the radial direction in the planar radial direction. If there is the displacement along the angular direction, azimuthal direction, that can be parameterized in this way. Anyway, the displacement along this radial direction is d rho. The magnitude of displacement along the angular direction, if it is a radius rho and we have angle d phi, then this magnitude of displacement is rho d phi. Okay, so gradient is the derivative with respect to coordinates, but it has the dimension of a length, not an angle, length. Therefore, if the coordinate is length, then you just take the radial direction, that is, take the derivative with respect to the radial direction. But if it is an angle, then you have the displacement length dimension to product of angle multiply the radius. So radius times angle, that is the displacement. So this length, you take the derivative with respect to length. Along the z direction, z is not an angle but just a distance scale, so this is length. Okay. These are simple examples. You apply the gradient operator to find the electric field, x, y, z component of the electric field, directly from the electrostatic potential. Uniformly charged wire longitudinal direction. We just have computed the electrostatic potential due to line charge. Electrostatic potential due to line charge from 0 to L has been obtained in here. By making use of that one, with doubling the size from minus L to L, we end up with this expression for the electrostatic potential for the uniformly charged wire. A little bit tedious calculation can be done to find the express value for the electric field out of the electrostatic potential. So because every calculation step is displayed explicitly, you can simply follow the calculation. This is longitudinal direction. The wire is in this direction. Longitudinal and perpendicular direction, that is transverse direction. So longitudinal direction component is obtained in here, and transverse fraction. We already computed the electric field around the wire by making use of the Gauss law. We introduced the Gaussian surface and we made use of the symmetry. Electric field is radial, and evaluated the electric field. Electric magnitude of the electric field must be constant on a surface of radius rho, and the same result can be obtained directly from the potential, electrostatic potential given in here, without applying the Gauss law. All right. Next, the electrostatic potential for the uniformly charged disk can also be obtained, also be used to compute the electric field. Electric field is minus gradient of potential, and substitute this potential in here. And derivative of this function is trivial. And you reproduce the electrostatic potential, the electric field, sigma over 2 epsilon 0, sigma over 2 epsilon 0, when the sheet is charged with the surface charge density sigma. We have already commented the electrostatic potential, and the system of charged particle can be computed in such a way: distance, product of charges over distance, and sum them all, multiply 1 over 4 pi epsilon 0. Electrostatic potential of a charged isolated conductor. These are key ideas involving a conducting object. An excess charge placed on a conductor will, in the equilibrium state, be located entirely on the outer surface. Equilibrium. There is no current flowing. Entire conductor, including interior points, is at a uniform potential. Inside the conductor, E equals 0, that means V equals constant. Very, very important. If an isolated charged conductor is placed in an external electric field, then at every internal point, the electric field due to the charge cancels the electric field, external electric field. So a combination of the internal distribution of charge and external electric field combination is to cancel the electric field inside the conductor. Here, a hollow metal sphere is charged to a potential V. The potential at its center is V, because inside the conductor electric field is 0, and the potential, electrostatic potential inside the conductor is always constant. We recall the electric field is sigma over 2 epsilon 0, left and right. If the charged plate is open, If it is a closed surface, just outside and inside, microscopic view, out, in, E field is 0, outside, epsilon, sigma of epsilon 0, instead of sigma over 2 epsilon 0. Here the flux goes to the left and right together, but inside the conductor, electric field must be 0, so this flux is doubled outside. Okay? Then, what is the charge? This uniform charge distribution, charge is surface charge density multiplied by the area of a sphere. That's 4 pi r squared. Because sigma is epsilon 0 electric field, we have this kind of expression. The potential on the surface relative r goes to infinity is then obtained in such a manner. It is just like the charge to bring to the radius r. Correct. Download the following paper by clicking the hypertext and answer the questions. You find the link and download the paper, and this paper computes the electrostatic potential and electric field due to a uniform charge distribution over a triangle. Even the triangular charge distribution contribution can be evaluated, and you'll find the integral that we have evaluated for the line charge. This integral is quite useful. Arcsine hyperbolic. This integral is universally used to find out the charge distribution over the space, especially it was used for the linear charge distribution, but it can also be used for the surface charge distribution. So it is quite useful formula. And do not copy the integral table, but you had better to train this explicit derivation of the integral table. Then it will be very easy to evaluate any other integrals in the future appearing in the physics problems. So today we have studied the electrostatic potential, and electrostatic potential is much easier to compute rather than the electric field, because the electrostatic potential is a scalar instead of a vector. And once you obtain the scalar value for the electrostatic potential, you take the derivative by applying minus gradient to find the electric field. That's it for today.